Fibonacci heap insert is very simple procedure. To insert an element in a Fibonacci heap, we just create a single node or singleton tree with one node that is to be inserted first, and then add this node to the root list. So for this example, suppose I want to insert 21, so I make a single node 21 as a singleton tree, and then add this node to this root list. So this node will be added anywhere in the root list. Because I have a circular doubly linked list, I can just change the pointers in order to add the node to the root list. Then after that I have to update the min pointer. So if I insert the information which is inserted here, if this information is instead of 21, if 1 is there, so suppose if I insert the information as 1, then that information, then the min pointer would be changed. So suppose here it is 1, then 1 is inserted here, then in the root list, because this is a minimum node, the min pointer will be pointing to here. Okay, now so this is a pseudo code for the fib heap insert. So if you want to insert an element in node heap h with the information x, then first we create a singleton tree. So this whole procedure will create a singleton tree by making this degree of x is 0, parent of x is null, child of x is null, left and right is pointing to same element because it is a circular doubly linked list, only one element is there. Then we concatenate the root list containing the node x with the root list with h. So the x node with the information 21 is concatenated to the heap which is already there, heap h. Now in this step we have to update the minimum. Initially the min of h, if the min of h is nil, then if we have the inserted key value is minimum, then the key value of min heap of h, if any of this condition is true, then we have to update it with the x, otherwise the min heap remain the same. And finally we have to add the number of nodes in a heap. So the number of nodes will be incremented by 1 when only one node is inserted. So as the x is added to the root list of h, the actual time taken by this operation is order of 1 because there is a circular doubly linked list. So node x become a single node heap order tree and thus an unordered binomial tree in the Fibonacci heap. It has no children and the node which is inserted is unmarked. So as we can see here, the node which is inserted is set as unmarked node. So let's take some analysis of insert operation. So as we see that let h be the Fibonacci input heap. So before the operation, insert operation, the h heap is there. After insertion, the heap is converted into h dash. So the potential function, we have to calculate the change in potential in order to analyze the performance. So let's find out the t of h dash. The number of trees is increased. Mark node will be remain the same. So the difference between phi of h dash and phi of h would be, this is t of h plus 2 into m of h. So t of h is t of h plus 1, and here is t of h plus 2 of mh. So the difference is equal to 1. So, and we know that the actual cost is also order of 1 because we just shift the pointers and changes in potential is 1. So the amortized cost is summation of change in potential and the actual cost. So order of 1 plus 1, it means order of 1 is the actual cost of the insertion. Now second operation is find out the minimum element in the tree. So as we know that the min of h is pointing to the minimum element in the root list, and each root node is a minimum in its tree. So we just need to fetch the min of h. In order to find out the minimum element, we need to fetch the min of h, which is we know already. So order of an actual time, we do not change the potential here, so amortized cost also order of 1. Next is binomial heap uniting operation. If you want to unite two Fibonacci heap then this is a procedure. So fib heap union, it will take h1 and h2 as two input heaps, and in this one first you create a auxiliary heap h, and then update the mean of this one with the mean of h1, and then concatenate the root list of h2 with the root list of h. So after after creating the fib heap, we need to just also copy the h1 into h, and then update the mean of h as a mean of h1. Okay, so this line also says that you just copy the h1 heap into the auxiliary array, then concatenate the root list of h2 with the root list of h, and we have to update the minimum pointer. Then so if this condition is this condition will check about the minimum pointer, and if it is found, if min of h is found greater, then it will be updated by h2. Then also we have to update the number of nodes in a heap, which is equal to number of nodes in h1 and number of nodes in h2. Then we free the object of h1 and h2 and return h. So let's see the example by fib heap union. So suppose we have two heaps given. So here the heaps given are h1. Suppose this is a h1 heap, this is h2. Okay, so both have some mean pointer in its root list. So to create a united Fibonacci heap, we create an auxiliary heap h and copy this h1 inside this one. So this h1 is copied here, and min is updated. So min of h is min of h1. So this is my min of h1, and this is min of h. Then we have to merge the root list of h2 with the root list of h. So the min of h is here. Now we just copy the root list here, and because in order to merge the root list, we just shift the pointers. So in this example, what I do, I just copy the right of x to 3, then I remove the left of x, which is linked to 7 here, because the 3 is already connected with the 17. Then 3 is the right of x would be 17, and 3 left of x would be 21. The 21 left of x is 21, right of x is 7, and 7 right of x is 23. That's why I make it circular. And then update the min of h, because this is the new root list. I will check with the min of h here. So the min of h is now 3, because it is the minimum element in my root list. Okay, so this is how we unite the two two Fibonacci heap in one Fibonacci heap. Okay, so let's analyze the performance. So the performance is analyzed by the potential function. So potential function of change in potential is we have phi of h after the operation, and we initially have two heaps, phi of h1 and h2. So this is the data structure after the operation, and this is the data structure before the operation. We have two data structure with h1 and h2. So we have to calculate the phi of h1 and phi of h2. So this is how we calculate. T of this one is T of h plus 2 of mh, this one is T of h1 plus 2 of mh1. Similarly, we can write like this, and the difference between these two is 0. Why? Because we know that T of h is nothing but summation of these two trees, and mark of node is nothing but number of mark nodes in h1 and number of mark nodes is h2. So the change in potential is 0. We do not change the structure of the heap, we just shift the pointers, because it is a circular doubly linked list. So the actual cost is order over, that is also the amortized cost, because the change in potential is 0 here. Okay, now next is, if you want to extract the minimum node, means we need to find out the minimum node, then delete it from the tree. So for that purpose, the fib heap extract min procedure is called, which is in which first we take a auxiliary pointer x, which is pointing to min of the heap, current min of the heap. Then we know we check that whether the z is not equal to null. Then if z is not equal to nil, then for each child of x of z, so we have to add x to the root list of h. So suppose in my Fibonacci heap, suppose this is the min pointer, min of h. Then if this pointer have 3 childs, so this is now pointing to here as a z. Then if you want to extract this node, then merge this child into the root list. So the root list will be updated as this. So we need to merge this child, so add each x into the root list. So this is a child list which is added to the root list. Okay. Then make the parent of each of the x as a nil, because it is in the root list now. Remove the z from the root list of h. We remove this z from the root list, and now if the z is equal to right of z, means if the if some case is there where z is the only node, because z is right of z, it means the node is pointing to itself. It means in circular doubly linkage only one node is there. So if z is the only node in the root list with no child, then we have to update the min of h with the nil, because that z would be deleted and the heap does not contain any node. That's why min of h is nil. Otherwise we have to update the min of h to the right of the z. So if min of h is here, then it will pointing to right of the z. So whatever, so suppose some node is here, z is here, and this is the right of z. If it is not a single node in my tree, then these 3 nodes is updated to the root list, and the min pointer is updated to the next of the z. Okay. Then we call the consolidate procedure on this whole heap, which is modified in this step. So this is the first modification in the data structure. So we need 2 modification. By this procedure, one modification is done. By consolidate, other modification is done. Okay. So the consolidate function is called on this modified heap. After that, after consolidation, we have to decrement the number of nodes as we have extracted or deleted one node from the tree. Okay. Now let's understand the consolidate function. In consolidate function, we have to maintain an auxiliary array ai with the degree of n of h, and this auxiliary array generally have the size log n base 2. Okay. Now for each of root list w, each node w in the root list of h, we need to scan the root list and check whether and store each node degree in d, and then from that degree we have to match in the auxiliary array. So this array is array of pointers, which is pointing to the nodes in the root list of the tree. So this array contain the pointers. So these are some pointers pointing to some node. So suppose the array is indexed from 0, 1, 2, 3. So these 0, 1, 2, 3 are the degrees. So for degree 0, if a node in the root list of degree 0, that is pointing by this index. If the root list is degree 1, then it is pointing by this index. So this auxiliary array is array of pointers which is pointing to those nodes with have the degree equal to the index of the corresponding pointer in the array. So in here, while a of d is not equal to nil, means a of, so suppose from is here, let's suppose d is equal to 0. If a of d means a of 0 does not pointing to any node, then what we do, we have assign a y pointer which is which have the value of a of d, and then if q of x is greater than q of y, then we have to exchange both and then call the fibbling procedure. Okay. Then we make the a of d as a nil and increment the value of d. So let's understand this whole consolidated function with the example. Okay, before that, this is a linking operation. Suppose you have two trees with the root node 15 and 3. So here 3 is a smaller root, 15 is a larger root. If you want to link these two trees, then the link procedure will make the smaller root as a root list of the combined tree, and then the other node with the larger root is added anywhere in the child list, because it is a circular doubly linked list. So the node can be added anywhere in any order. So in binomial heap, what we do, we just add this node in the leftmost manner. In Fibonacci heap, the node can be added anywhere. So let's demonstrate. This is a demonstration about the delete min or extract min operation. So suppose in this is a Fibonacci heap given as h, in which this is a min of h. So to delete min, we extract this node 3 from the root list and meld its children into the root list and update the min pointer. Okay, so what we does, these are the childrens, we just meld the children into the root list and update the pointer. So the pointer, update pointer would be the min of h, now nothing but right of x. So if x is a minimum node, the min would be the right of x. So right of x is 7. So the updated min of h would be pointing to the node 7. Then we consolidate the tree so that no two roots have the same rank or same degree. So we apply the consolidation function on this heap h. So this is the first change in the data structure, change in the potential. Okay, so then we apply the h on this modified version of heap. So for the consolidation, we require an auxiliary array, as we know that this is auxiliary array A, these are the degree D, and these are the pointers. So we start with the initial node, we have to scan the root list. This is the W and X pointer as mentioned here. This is the X and W pointer. So for each W, we have to update X. Okay, so we have to check the degree of this W. So degree of this W is 1. So by this index, this is pointing by A of 1. Okay, because the degree is 1. Similarly, scan next node, the degree is 2, it is pointing by A of 2. The degree of is 0 in the next node, so it is pointing by A of 0. Now as we see that now A of D is not equal to nil in the next at node 17, because A of D is not equal to nil, what we have to do, we have to update a pointer y. So y is here, we have to update a pointer y. Pointer y is pointing to previous node of x. Okay, so then we check whether the key of x and key of y, which is minimum. So 17 is minimum. So if 17 is minimum, then if x key is greater, then only we can exchange. If it is lesser, then we do not need to exchange. We just link these two procedures. So we have to link, call the fib heap link with on h with y and x. It means the x would be the parent node. So let's see now here, x would be the parent node, and this y would be here. Okay, again because here again because A of D is not equal to nil. Now 1 is already filled, A of D is not equal to nil. So we assign A of D as a y. So y is pointing to the already pointed information. Then again we have to check the x and y. So in x and y, because y is lesser, we have to exchange the x and y. So x is pointing to the node and y is pointing to this node. After exchange, we just call the fib heap link. X would be the parent and y will be the child. Now the degree of x is 2 now. 2 is also not nil. So again it is while loop is executed. So we have to link this 24, because this 24 is now pointed by y and this is x. Okay, so which is minimum? 7 is minimum, no need to exchange, just link these two nodes. So we just link these two nodes and it is pointing by 3. Now update the w and x. Now w and x, a of d is not equal to nil, so a of d is nil. Now a of 1 is free, so degree is 1, a of 1 is free, just pointing it. Again next is a of 0 is also free, just pointing it. A of 1, so a of 1 is already busy, so it will execute in the while loop. Y is updated, check whether a of y and x, so y is lesser, so we exchange the x and y, so y is pointing here and x is pointing here after exchange, and this 41 is linked to the 18. Okay, so x is here, y is here, and it is linked. Now again it is pointing by a of 2. Now there is no right node here, so x would be the root list is over, that's why the procedure is closed. So this is the consolidation procedure. After the consolidation we have to update the min pointer. So this procedure from 15 to 19 will update the minimum pointer in the root list of the modified tree. Okay, so this is the modified tree. After the consolidation operation we just scan the root list and update the minimum pointer. So the minimum pointer is here 7. Okay, so this procedure is also given in the book Corman. I will take this procedure from that book, so you can go through the book and you can also check it. Now this is all about the delete min operation. Now for the analysis purpose we need to calculate the potential function. So as we can see that we require in this whole amortized analysis we have two configurations in our data structure. First is when we extract the minimum node and add it to the root list. So if this is my minimum node, then all children are added to the root list, then we call the consolidate function. So the consolidate function, because the consolidation the maximum tree that can possible is the degree of n plus t of h minus 1. The degree of n means the degree of that node, because min of h, suppose the degree of a node is the maximum degree of a heap. Okay, so the degree of that node means 3 plus number of trees in a heap. So suppose 3 trees are in a heap, minus 1 means you have to delete this node and add this, so you have to negate this one node. Okay, so your tree can be, for the consolidation, your tree can be at most this much of size, d of n plus t of h minus 1. So you can say that for the consolidation you require order of d of n plus t of h tree. At most that much of tree is possible. Secondly, for the potential function for the extract min is you require t of h. So before extract min this is the potential function. After extract min there may be d of n plus 1 plus 2 of mh 1, because at most we have dn plus 1 root. So as we can see in an example, my tree have the degree of the whole degree is 3 and the root have 3 nodes. So we can have only 4 nodes in my root list after the extract min operation. So after the operation is done, you cannot have t of h greater than d of n plus 1. You cannot have tree more than this. Okay, this is a mathematically proof theorem. So the amortized cost includes the change in potential. So the change in potential here is at two steps. First, when consolidate function is there, this is a potential, and when extract min is there, this is a potential. Okay, so we have to add this potential and decrement from the original potential. So when you add it, so it is converted into d of n plus order of th minus t of h, that is order of d of n. So the order of d of n means order of log n, because d of n never be greater than always less than log of n. So the time complexity of the delete min analysis is order of log of n. Okay, so this is all about the Fibonacci heap delete min operation. Thank you very much.